Imagine peering back 13 billion years, through cosmic fog so thick it swallowed light itself. The James Webb Space Telescope just pierced that veil, revealing a secret starburst in the cradle of the universe. These hidden stars, forgotten by time, were building galaxies 10 times larger than we ever imagined, their glow trapped in ancient dust clouds. The first galaxies weren't tiny, scrappy clusters but sprawling, luminous islands of starlight, forged in a cosmic frenzy. How did we miss them? Because they hid in plain sight, veiled by the very gas and dust that birthed them. Webb's infrared eyes sliced through the haze, uncovering a universe that started not with quiet whispers, but with a deafening roar of star formation. This isn't just rewriting history, it's forcing us to rethink everything we thought we knew about the dawn of galaxies. The James Webb Space Telescope has uncovered a surprising truth about the dawn of the universe: the very first galaxies were far larger than previously imagined. For decades, scientists believed that the earliest galaxies, formed just a few 100 million years after the Big Bang, were small, faint, and scattered across the cosmos. But now, using its unprecedented power to peer through cosmic dust and detect light from the earliest stars, Webb has revealed that these ancient galaxies were not only more massive but also formed in a way that challenges our understanding of how the universe evolved. This discovery isn't just about size, it's about rewriting the story of how the universe built its first structures, and what that means for the stars and galaxies we see today. To grasp why this matters, we need to step back to the universe's infancy. Just 13.8 billion years ago, the cosmos was an almost impenetrable fog of gas and darkness. Over time, gravity pulled together fragments of matter, eventually giving rise to the first stars. These stars, born from clouds of hydrogen and helium, were massive, often hundreds of times the size of our Sun, and burned brightly before collapsing into black holes or exploding as supernovae. But until Webb's arrival, scientists had struggled to observe these early stars directly. The light they emitted had traveled billions of years to reach us, stretched into the infrared spectrum by the expansion of the universe. Earlier telescopes, like Hubble, could detect this light, but they often couldn't see through the thick clouds of dust that obscured the earliest galaxies. Webb, with its advanced infrared instruments, has changed that. The key to this discovery lies in Webb's ability to detect light from the earliest stars that were hidden behind dense clouds of dust in the nascent universe. These stars, which formed in the first few 100 million years after the Big Bang, were not just numerous, they were also clustered in massive, sprawling structures. Previous observations had suggested that these early galaxies were small, perhaps only a few thousand light-years across, similar in size to the Milky Way's satellite dwarf galaxies. But Webb's data reveals a different picture. The telescope has identified galaxies that are at least 10 times larger than previously thought, some stretching over 100,000 light-years in diameter. These galaxies are not just bigger, they're also more massive, containing hundreds of billions of stars, many of which are the massive, short-lived stars that dominated the early universe. How did Webb uncover these hidden stars? The answer lies in the way light behaves across cosmic time. When light from the early universe travels billions of years to reach us, it is stretched into longer wavelengths, a phenomenon known as redshift. This means that the light from the first stars, which originally emitted visible light, now appears as infrared radiation. Webb's instruments are specifically designed to capture this infrared light, allowing it to peer through the dust that had previously blocked our view. By analyzing the faint, redshifted glow of these ancient stars, scientists have been able to map out the structure of the first galaxies with remarkable clarity. What they found was astonishing: these galaxies were not isolated, scattered islands of star formation. Instead, they were vast, interconnected systems, possibly even the precursors to the massive galaxy clusters we see today. But why did earlier observations miss these galaxies? The answer has to do with the limitations of previous telescopes. Hubble and other space-based observatories could detect the faint light of these early stars, but they often struggled to resolve the details of their structure. The dense dust clouds surrounding these galaxies absorbed much of the visible light, making them appear dimmer and more diffuse. Webb's advanced infrared sensors, combined with its larger mirror and improved technology, have allowed scientists to peer through this dust and see the galaxies in their full, luminous glory. The result is a dramatic shift in our understanding of the early universe. These galaxies were not just bigger, they were also more complex, with intricate networks of star-forming regions that suggest a more dynamic and interconnected cosmos than previously thought. the implications of this discovery are profound. For years, scientists have debated how the first galaxies formed. Some theories suggested that they began as small, isolated systems that gradually merged over time. Others proposed that they formed in massive, rapid bursts of star formation. Webb's findings seem to support the latter idea. The newly discovered galaxies appear to have formed in a single, intense episode of starbirth, creating structures that were both massive and structured. This challenges the notion that the first galaxies were simple, low-mass systems. Instead, they may have been the seeds of the massive galaxies we see today, laying the foundation for the cosmic web of galaxies that now stretches across the universe. But the story doesn't end there. The discovery of these hidden stars also raises new questions about the role of dark matter in galaxy formation. Dark matter, an invisible substance that makes up most of the universe's mass, is thought to have played a critical role in shaping the early cosmos. However, the exact mechanisms by which dark matter influenced the formation of the first galaxies remain unclear. The newly discovered galaxies, with their massive size and complex structure, may provide clues about how dark matter interacted with visible matter in the early universe. If these galaxies formed in the presence of large dark matter halos, it could mean that dark matter was more actively involved in shaping the universe's structure than previously believed. Another intriguing possibility is that these early galaxies were not just massive, they were also incredibly efficient at forming stars. The rate at which stars formed in these galaxies was far higher than in later galaxies, suggesting that the early universe had a different recipe for star formation. This could be due to the unique conditions of the early cosmos, such as the abundance of primordial gas or the presence of massive, short-lived stars that contributed to rapid star formation. Understanding these processes is crucial for building accurate models of how the universe evolved from its earliest moments to the present day. The discovery also has broader implications for our understanding of the universe's timeline. If the first galaxies formed earlier and were more massive than previously thought, it could mean that the universe reached a certain level of complexity much sooner than we believed. This would affect our estimates of when the first stars formed, how quickly galaxies merged, and even how the cosmic web of galaxies took shape. It also raises questions about the role of feedback mechanisms, such as supernovae and black holes, in regulating star formation in the early universe. These processes, which are well understood in later galaxies, may have played an even more significant role in the earliest epochs. For scientists, this discovery is a reminder of how much remains to be learned about the universe's origins. The James Webb Space Telescope has already revolutionized our ability to observe the early cosmos, but its findings are just the beginning. As researchers continue to analyze the data, they may uncover even more surprises, perhaps even galaxies that predate the ones already discovered, or entirely new mechanisms for star formation. The universe, it seems, is far more complex and dynamic than we ever imagined. In the end, the discovery of these hidden stars and their role in forming the first massive galaxies is more than just a correction to our understanding of the universe's history. It is a testament to the power of human curiosity and the relentless pursuit of knowledge. By peering back in time to the universe's infancy, we are not just learning about the past, we are gaining insights into the very nature of existence. The stars we see in the night sky today are the remnants of these ancient, hidden stars, their light traveling across billions of years to illuminate our understanding of the cosmos. And with each new discovery, we come one step closer to unraveling the mysteries of the universe's origins. For decades, astronomers have gazed into the cosmos, peering through the veil of time to glimpse the earliest moments of the universe. But the first galaxies, those ancient, flickering seeds of star formation, remained elusive, shrouded in the cosmic fog of the early universe. Now, the James Webb Space Telescope has begun to peel back that veil, revealing a startling truth: the first galaxies were far larger and more complex than previously imagined. But how did scientists arrive at this discovery? What tools, methods, and perseverance led them to this revelation? Let's trace the journey of how the James Webb Space Telescope uncovered these hidden stars, and how they reshaped our understanding of the universe's infancy. The James Webb Space Telescope, launched in 2021, is a marvel of engineering and science. Its primary mission was to study the early universe, seeking out the first galaxies to form after the cosmic dark ages. But the universe is vast, and the light from these ancient galaxies has traveled billions of light-years to reach us. By the time it arrives, it's stretched into the infrared spectrum, a wavelength of light that human eyes cannot see. This is where Webb's infrared capabilities become critical. Its advanced instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, are designed to capture this faint, redshifted light. These instruments are not just tools, they are the keys to unlocking the secrets of the universe's earliest epochs. However, detecting the first galaxies is no simple task. These ancient structures are incredibly faint, their light dimmed by the vast distances they've traveled. Moreover, the universe was still in its infancy when these galaxies formed, meaning they were surrounded by a thick veil of intergalactic gas and dust. This made them difficult to observe, as their light was scattered and absorbed. For years, astronomers relied on ground-based telescopes and earlier space observatories, like the Hubble Space Telescope, to study the early universe. But even with their capabilities, these instruments struggled to capture the faintest details of the first galaxies. The James Webb Space Telescope, with its larger mirror and advanced technology, was built to overcome these limitations. Its mirror, nearly 3 times larger than Hubble's, collects more light, allowing it to detect fainter objects. But even with this advantage, the process of finding these hidden stars was a complex and painstaking endeavor. The first step in this journey was to identify potential candidates for the earliest galaxies. Astronomers used data from previous surveys, such as the Hubble Deep Field, to pinpoint regions of the sky where the first galaxies might be located. These regions were chosen based on their distance from Earth and the likelihood of containing ancient, luminous structures. Once these targets were identified, the James Webb Space Telescope was directed toward them, its instruments calibrated to capture the faintest possible signals. The process of collecting data was slow and methodical. Each observation required precise alignment, and the telescope's instruments had to work in harmony to filter out background noise and isolate the faint light of distant galaxies. Every image captured by Webb was a mosaic of data, each pixel representing a tiny fragment of the universe's history. But even with the telescope's advanced capabilities, the data was not immediately clear. The first galaxies were not bright, luminous beacons but rather faint, diffuse structures. Their light was spread out over vast distances, making them difficult to distinguish from other cosmic phenomena. To make sense of this data, scientists employed sophisticated algorithms and machine learning techniques. These tools helped to identify patterns in the data, distinguishing between genuine galaxies and other sources of light, such as foreground stars or distant quasars. The process was like sifting through a vast ocean of light, searching for the faintest whispers of ancient stars. Each discovery required careful analysis, cross-referencing with existing data, and sometimes re-examining previous observations with new insights. One of the key breakthroughs came with the detection of specific types of stars that had been hidden from view. These stars, known as population 3 stars, are thought to have formed in the earliest moments of the universe, composed almost entirely of hydrogen and helium. They are massive, short-lived, and extremely luminous, but their light was difficult to detect due to their faintness and the vast distances they had traveled. However, the James Webb Space Telescope's ability to capture infrared light allowed scientists to detect the faint glow of these stars, even as they faded into the cosmic background. By analyzing the light emitted by these stars, researchers could determine their composition, age, and distribution within the first galaxies. This provided crucial evidence that these stars were not only present but were playing a significant role in the formation and evolution of the earliest galaxies. The process of confirming these findings was equally rigorous. Scientists had to rule out alternative explanations for the observed light. For example, the light could have been emitted by other types of stars or by the accretion of material around supermassive black holes. To address this, researchers used multiple instruments on the James Webb Space Telescope to cross-verify their observations. The NIRCam and MIRI instruments, for instance, provided complementary data, allowing scientists to study the same objects in different wavelengths. This multi-wavelength approach helped to build a more complete picture of the galaxies and their stellar populations. Additionally, the telescope's spectroscopic instruments were used to analyze the chemical composition of the light, revealing the presence of elements that could only have formed in the interiors of massive stars. These findings provided strong evidence that the stars detected were indeed the ancient population 3 stars, and that they were contributing to the growth of the first galaxies. The timeline of this discovery is as fascinating as the findings themselves. The James Webb Space Telescope was launched in 2021, and its first major observations began shortly after. In the months that followed, scientists began to process the data, gradually uncovering new insights about the early universe. The initial results, released in late 2022, hinted at the presence of massive galaxies forming earlier than previously thought. But it was only with continued observations and analysis that the full picture began to emerge. By 2023, researchers had identified several galaxies that were not only older than previously believed but also significantly larger in size. These galaxies, some of which were formed just 200 million years after the Big Bang, contained a vast number of stars, suggesting that the process of galaxy formation was more rapid and efficient than earlier models had predicted. The implications of these findings are profound. The discovery of these hidden stars challenges existing theories about how the first galaxies formed. Previously, scientists believed that the first galaxies were small, sparse collections of stars, gradually growing over millions of years. But the James Webb Space Telescope's observations suggest that these galaxies were already massive and complex, with a significant number of stars forming in a short period. This raises new questions about the role of dark matter in galaxy formation, the efficiency of star formation in the early universe, and the conditions that allowed such rapid growth. These findings also highlight the importance of the James Webb Space Telescope in pushing the boundaries of our understanding of the cosmos. The journey to uncover these hidden stars was not without its challenges. The data collected by the James Webb Space Telescope is vast, requiring immense computational power to process and analyze. Scientists had to develop new algorithms and techniques to handle the sheer volume of information, ensuring that no detail was overlooked. Additionally, the telescope's location in space, about 1.5 million kilometers from Earth, meant that any data transmitted back had to be carefully managed, with delays and bandwidth limitations requiring meticulous planning. Despite these challenges, the team behind the James Webb Space Telescope demonstrated remarkable perseverance, working tirelessly to refine their methods and interpret the data with precision. As the observations continued, the scientific community began to piece together a more accurate picture of the early universe. The James Webb Space Telescope's ability to detect faint light and analyze the chemical composition of distant galaxies has opened new avenues of research. Scientists are now exploring how these ancient galaxies interacted with their surroundings, how they contributed to the formation of larger structures, and what role they played in the eventual formation of the Milky Way and other galaxies. These questions are not just academic, they are fundamental to understanding the origins of the universe and our place within it. In the end, the discovery of these hidden stars is a testament to the power of human curiosity and technological innovation. The James Webb Space Telescope, with its advanced instruments and meticulous methods, has allowed scientists to peer into the cosmos and uncover secrets that were once thought impossible to detect. The journey to find these hidden stars was a complex and collaborative effort, spanning years of preparation, observation, and analysis. And as the data continues to pour in, it promises to reveal even more about the universe's earliest moments, challenging our understanding and expanding the horizons of scientific discovery. The James Webb Space Telescope has revealed a surprising truth about the early universe: the first galaxies were far larger than previously imagined. This discovery challenges long-held assumptions about how galaxies formed and evolved, offering a deeper glimpse into the cosmos' infancy. But why does this matter? To understand the significance, we need to revisit the fundamental processes that shaped the universe after the Big Bang. In the first few 100 million years, the universe was a vast, dark expanse filled with hydrogen and helium gas, scattered by the cosmic microwave background. Without the light of stars, the universe was a cold, silent void. Yet, within this emptiness, gravity began to act as the universe's invisible hand, drawing gas together into dense clumps. These clumps eventually collapsed under their own weight, giving birth to the first stars and the galaxies they would form. But how did these galaxies grow so large so quickly? Traditional models suggested that the earliest galaxies were small, fragmented, and scattered across the cosmos. They were thought to be the building blocks of the larger galaxies we see today, like the Milky Way. However, the James Webb Space Telescope's infrared eyes have pierced through the veil of time, revealing a different story. By observing the faint, redshifted light of ancient galaxies, the telescope has detected hidden stars that were previously obscured by dust and gas. These stars, forming in dense, massive regions, contributed to the creation of galaxies that are not only larger but also more complex than earlier theories predicted. This discovery is not just about size, it's about the very mechanisms that drove the universe's evolution. For decades, scientists have studied the formation of galaxies through telescopes like the Hubble, which could peer into the early universe but was limited by its optical capabilities. The James Webb Space Telescope, with its advanced infrared instruments, can see further and deeper, capturing light that has traveled billions of years to reach us. This light, stretched by the universe's expansion, reveals details about galaxies that were once invisible. The hidden stars detected by Webb are part of a process called starburst, a period of intense star formation that occurred in the early universe. These starbursts, fueled by the abundance of gas and the gravitational pull of dark matter, may have accelerated the growth of the first galaxies. Dark matter, an invisible substance that makes up most of the universe's mass, played a crucial role in this process. While it doesn't interact with light, its gravitational influence shaped the distribution of gas, creating the scaffolding for galaxies to form. If the first galaxies were larger, it suggests that dark matter's role was more significant than previously thought, or that the gas was more concentrated in these early structures. This challenges existing models of galaxy formation, which often assumed a more gradual, fragmented process. The James Webb Space, however, has provided evidence that some galaxies formed rapidly, perhaps in a single burst of activity. This rapid formation could have implications for how we understand the timeline of the universe's evolution. If the first galaxies were massive and formed earlier, it might mean that the process of star formation and galaxy growth was more efficient than previously believed. This efficiency could be due to factors like the density of gas in these early regions, the influence of dark matter, or even the role of feedback mechanisms that regulated star formation. For example, the energy released by massive stars could have influenced the surrounding gas, either accelerating or slowing down the formation of new stars. These feedback loops are still not fully understood, but the James Webb's observations suggest that they played a critical role in shaping the first galaxies. The discovery also has broader implications for our understanding of the universe's history. If the first galaxies were larger and more numerous, it could affect how we model the distribution of dark matter and the formation of larger structures like galaxy clusters. It might also influence our understanding of how the universe transitioned from a smooth, uniform state to the complex web of galaxies we see today. The James Webb Space Telescope's ability to detect these hidden stars is a testament to the power of modern technology in unraveling the cosmos mysteries. By peering into the infrared spectrum, the telescope can observe objects that are too distant or too obscured for other instruments. This capability has allowed scientists to see galaxies that formed just 200 million years after the Big Bang, a time when the universe was still young and gas-rich. These galaxies, once hidden, now reveal a story of rapid growth and intense activity. The significance of this discovery lies not just in the size of the galaxies but in the implications for our understanding of cosmic evolution. It suggests that the universe's early history was more dynamic and complex than previously thought. The formation of the first galaxies may have been a more rapid, coordinated process, driven by the interplay of gravity, dark matter, and the properties of the early universe. This challenges scientists to refine their models and consider new possibilities for how galaxies formed. For instance, some theories suggest that the first galaxies may have formed in a different way than previously assumed, perhaps through the merging of smaller structures or the collapse of massive gas clouds. The James Webb's observations provide clues that could support or refute these theories, pushing the boundaries of our knowledge. As we continue to analyze the data from the James Webb Space Telescope, we are not just learning about the past, we are gaining insights into the fundamental forces that shape the universe. The discovery of hidden stars and larger galaxies is a reminder that the cosmos is full of surprises, and that our understanding of it is constantly evolving. Each new observation brings us closer to answering the question of how the universe began and how it has changed over billions of years. The James Webb Space Telescope's findings are a crucial step in this journey, offering a glimpse into the universe's earliest days and challenging us to rethink the story of its creation. For centuries, humanity has gazed at the night sky, wondering about the origins of the universe. But it wasn't until the 20th century that we began to piece together the story of how galaxies formed. The Big Bang Theory, first proposed in the 1920s and refined over decades, laid the foundation for understanding the universe's infancy. Yet, even as scientists developed theories about the early cosmos, the tools to observe it remained limited. Until the 1990s, our view of the distant universe was constrained by the technology of the time. The Hubble Space Telescope, launched in 1990, marked a turning point. For the first time, astronomers could peer beyond our galaxy and study objects millions of light-years away. But Hubble had its limits. Its optical instruments could only capture visible light, making it difficult to see the faintest, most distant galaxies. These early galaxies, formed just a few 100 million years after the Big Bang, were shrouded in dust and emitted light in the infrared spectrum, a wavelength Hubble couldn't easily detect. So, while Hubble revealed thousands of galaxies in the early universe, it couldn't fully unravel their secrets. The next leap came with the James Webb Space Telescope, launched in 2021. Designed to operate in the infrared, Webb could see through cosmic dust and capture light from the universe's earliest days. But even with Webb's advanced capabilities, the discovery of hidden stars reshaping our understanding of the first galaxies wasn't just about new technology, it was the result of decades of scientific curiosity and incremental progress. Let's trace how our knowledge evolved, from the earliest theories of galaxy formation to the groundbreaking revelations of the James Webb Space Telescope. In the 1960s, astronomers like Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation, a faint glow left over from the Big Bang. This finding confirmed the universe was once a hot, dense state and provided a blueprint for how it expanded. But the question remained, how did galaxies form from this primordial soup? Theories in the 1970s and 1980s suggested that gravity pulled gas and dark matter together, eventually forming the first stars and galaxies. However, these models lacked direct observational evidence. The Hubble Space Telescope, launched in 1990, began to change that. By the mid-1990s, Hubble's deep field images revealed thousands of galaxies in a tiny patch of sky, many dating back to the universe's first few billion years. These observations showed that galaxies were already forming much earlier than previously thought, but they also raised new questions. The galaxies Hubble saw were smaller, more scattered, and less massive than expected. Scientists wondered if these early galaxies were the precursors to the vast, structured systems we see today or if they were somehow different. The answer, it turned out, required looking even further back in time. In the 2000s, astronomers developed new techniques to study the early universe, including using the Spitzer Space Telescope, which operated in the infrared. Spitzer's observations hinted at the presence of massive, dusty galaxies forming in the early cosmos. But these findings were still limited by the technology of the time. The James Webb Space Telescope, with its larger mirror and advanced infrared instruments, was built to overcome these limitations. Its primary goal was to study the first galaxies, stars, and planets that formed in the universe's infancy. Yet, even with Webb's capabilities, the discovery of hidden stars wasn't just about new technology, it was the culmination of decades of scientific inquiry. For years, astronomers had debated how the first galaxies formed. Some theories suggested they were small, isolated systems, while others proposed they were massive, rapidly forming structures. The James Webb Space Telescope's ability to detect infrared light allowed it to peer through cosmic dust and observe galaxies that were previously invisible. But the data from Webb revealed something unexpected: these early galaxies contained more stars than anticipated. The hidden stars, detected through their infrared signatures, were forming at an accelerated rate, contributing to the rapid growth of these ancient galaxies. This finding challenged previous assumptions about the timeline and scale of galaxy formation. Earlier models had predicted that the first galaxies would be smaller and more diffuse, but Webb's observations showed that they were already massive and structured. The key to understanding this shift lies in the role of star formation in the early universe. Stars are the building blocks of galaxies, and their formation is influenced by factors like gas density, temperature, and the presence of dark matter. In the early universe, conditions were different: gas was denser, and the universe was still expanding rapidly. These conditions may have allowed stars to form more efficiently, leading to the rapid buildup of massive galaxies. But how did scientists come to realize that these hidden stars were playing such a crucial role? The answer lies in the evolution of observational techniques. In the 1990s, Hubble's images of distant galaxies showed faint, irregular structures, but they lacked the resolution to study their internal composition. By the 2010s, advancements in infrared astronomy, including the use of ground-based telescopes and space observatories like Spitzer, allowed scientists to detect the faint glow of distant galaxies. These observations suggested that the first galaxies were not as small as previously thought, but the full picture remained elusive. The James Webb Space Telescope's ability to capture high-resolution infrared images provided the missing piece. Its advanced instruments, including the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, allowed astronomers to peer deeper into the universe than ever before. These instruments could detect the faintest light from the earliest galaxies, revealing details about their structure, composition, and star formation rates. The data from Webb's first observations, released in 2022, confirmed that the first galaxies were already massive and complex. But the discovery of hidden stars took this understanding even further. These stars, which had been obscured by dust and gas in the early universe, were forming at an unprecedented rate. Their presence explained how galaxies could grow so quickly, challenging previous models that assumed slower, more gradual formation. This finding wasn't just a technical breakthrough, it was a paradigm shift. It forced scientists to reconsider the timeline of galaxy formation and the role of star formation in shaping the universe. The implications extend beyond the early universe. Understanding how the first galaxies formed is crucial for studying the evolution of the cosmos. These ancient galaxies laid the foundation for the structures we see today, influencing the distribution of dark matter, the formation of supermassive black holes, and the eventual emergence of the universe as we know it. But the journey to this discovery wasn't linear. Each step forward was built on the work of previous generations of scientists. The development of the James Webb Space Telescope itself was a decades-long effort, driven by the need to overcome the limitations of earlier instruments. The telescope's design, including its large mirror and cryogenic cooling system, was the result of years of engineering and scientific collaboration. Similarly, the analysis of Webb's data required new computational techniques and theoretical models to interpret the complex signals from the early universe. This interplay between technology and theory is what has allowed us to make such groundbreaking discoveries. The James Webb Space Telescope's findings about hidden stars and massive early galaxies are a testament to the power of scientific curiosity and technological innovation. They remind us that our understanding of the universe is always evolving, shaped by new observations and the courage to question long-held assumptions. As we continue to analyze Webb's data, we may uncover even more surprises about the early universe. These discoveries not only deepen our knowledge of galaxy formation but also shed light on the fundamental processes that shaped the cosmos. The story of the James Webb Space Telescope is not just about a single mission, it's about the collective effort of scientists, engineers, and thinkers who have dedicated their lives to unraveling the mysteries of the universe. And as we look to the future, the next chapters of this story will undoubtedly bring even more revelations, expanding our understanding of the cosmos and our place within it. The James Webb Space Telescope has revolutionized our understanding of the early universe, revealing a startling truth: the first galaxies were far more massive and complex than previously imagined. But as scientists pore over these groundbreaking images, a new wave of questions emerges. How did these ancient galaxies form so quickly? What hidden forces shaped their growth? And why did earlier observations miss them entirely? These are not just technical puzzles, they're fundamental challenges to our understanding of cosmic evolution. The universe's first galaxies, formed when the cosmos was only a few 100 million years old, were once thought to be small, sparse collections of stars. Now, the James Webb's infrared vision has uncovered a different story, one where dense, luminous galaxies emerged in a cosmic blink, defying expectations. Yet, this revelation has only deepened the mystery. If these galaxies were so massive, how did they form so rapidly? What mechanisms allowed them to accumulate such vast numbers of stars in such a short time? And why were they hidden from earlier telescopes? These questions lie at the heart of a scientific debate that is as much about the limits of our technology as it is about the universe's own secrets. The James Webb's ability to peer through cosmic dust has unveiled these galaxies, but it has also exposed gaps in our models of star formation and galaxy evolution. Scientists are now grappling with a new reality. The early universe may have been far more dynamic and complex than we ever anticipated. One of the most pressing questions is how these galaxies managed to form so quickly. The universe was only a few 100 million years old when these galaxies began to take shape, yet they already contained hundreds of millions of stars. How did such a staggering number of stars form in such a short time? Traditional models of star formation suggest that massive stars form in dense molecular clouds, but the conditions in the early universe were vastly different. The primordial gas was hotter, more diffuse, and filled with heavier elements, ingredients that could have influenced the rate at which stars formed. Some scientists speculate that the first galaxies may have formed in regions of extreme density, where gravity pulled gas together with such force that stars ignited almost instantaneously. Others argue that the presence of dark matter played a crucial role. Dark matter, which makes up most of the universe's mass, may have provided the gravitational scaffolding necessary to collapse gas into massive structures. Yet, the exact interplay between dark matter and visible matter remains unclear. If dark matter halos acted as cosmic seeds, how did they evolve into the massive galaxies we now observe? And if these galaxies were so large, did they form through mergers of smaller galaxies, or did they grow from the start? These are questions that continue to divide researchers. Another mystery lies in the hidden nature of these stars. Earlier telescopes, like the Hubble Space Telescope, struggled to see through the thick clouds of dust that obscured the earliest galaxies. But the James Webb's advanced infrared capabilities have allowed it to peer through this veil, revealing stars that were previously invisible. Yet, this discovery raises a new question: why were these stars hidden in the first place? Was it simply a matter of dust, or did other factors play a role? Some scientists suggest that the early universe was filled with a different kind of dust, composed of heavier elements that could have scattered light in unique ways. Others propose that the stars themselves were intrinsically different. Perhaps they were much hotter or more massive than the stars we see today, making them difficult to detect with older instruments. But if these stars were so different, how did they form? And what does their existence tell us about the chemical composition of the early universe? These are not just technical challenges, they're profound questions about the very nature of star formation. The James Webb's observations have also sparked a debate about the role of feedback mechanisms in galaxy formation. In the early universe, the process of star formation was likely more chaotic. Massive stars, when they formed, would have exploded as supernovae, releasing energy that could either suppress or accelerate further star formation. But how did these feedback loops play out in the first galaxies? Did the energy from these explosions help regulate the growth of massive stars, or did they trigger a chain reaction that led to even more rapid star formation? Some researchers argue that the presence of supermassive black holes in these early galaxies may have played a key role. These black holes, which can weigh millions or even billions of times the mass of the Sun, are thought to have formed alongside their host galaxies. But how did they grow so quickly? Did they form from the collapse of massive stars, or did they arise from some other, more exotic process? The connection between supermassive black holes and their host galaxies remains one of the greatest mysteries in astrophysics. If these black holes were already present in the earliest galaxies, what does that say about the timeline of their formation? And if they played a role in regulating star formation, how did they influence the growth of these massive galaxies? These questions are not just academic, they have profound implications for our understanding of the universe's evolution. The James Webb's discoveries have also raised questions about the distribution of these early galaxies. Previously, scientists believed that the first galaxies were scattered across the cosmos, forming in isolation. But the James Webb's observations suggest a different picture. Some of these galaxies appear to be clustered together, hinting at a more interconnected early universe. If these galaxies formed in groups, what does that mean for our understanding of large-scale structure? Did they form in dense regions of dark matter, or did they emerge from some other kind of cosmic web? And if they were clustered, did they influence each other's growth, or did they evolve independently? These questions challenge the prevailing models of galaxy formation and suggest that the early universe may have been far more dynamic and complex than previously thought. Yet, for all these revelations, there are still gaps in our understanding. The James Webb has given us a glimpse into the past, but it has not provided all the answers. Some scientists argue that the observed galaxies may not be as massive as they seem. Could the James Webb's instruments have overestimated their size? Or is there a different explanation for the apparent brightness of these galaxies? Others question whether the observed galaxies are truly the first to form, or if they are simply the most luminous ones that we have been able to detect. These uncertainties highlight the limitations of even the most advanced telescopes. The James Webb is a marvel of engineering, but it is still bound by the constraints of its instruments and the physics of light. There is always the possibility that our observations are incomplete, or that the universe has surprises that we have yet to uncover. And then there is the question of what these findings mean for the future of astronomy. The James Webb's discoveries have already sparked new research directions, but they also raise the need for even more powerful instruments. Future missions, such as the Euclid Telescope or the Nancy Grace Roman Space Telescope, may provide the data needed to resolve these mysteries. But until then, scientists must continue to refine their models, test their hypotheses, and push the boundaries of what we know. The James Webb's revelations about the first galaxies are not just a triumph of technology, they are a reminder of how much we still have to learn. The universe, in all its vastness and complexity, continues to challenge our understanding. And as we look deeper into the cosmos, we may find that the answers to these questions are as surprising as the questions themselves. James Webb Space Telescope finds hidden stars, making the universe's first galaxies much bigger than we knew. This part of our deep dive into James Webb Space Telescope finds hidden stars, making the universe's first galaxies much bigger than we knew focuses on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The James Webb Space Telescope has rewritten our understanding of the universe's earliest days. For years, astronomers believed the first galaxies were small, clumpy collections of stars formed in the universe's infancy. But Webb's infrared vision has pierced through cosmic dust and revealed something astonishing: hidden stars buried in the earliest galaxies, fueling their rapid growth. These stars, invisible to earlier telescopes, are now being counted in vast numbers, suggesting the first galaxies were not just bigger than we thought, they were massive, sprawling structures that formed within the first few 100 million years after the Big Bang. This discovery challenges long-held models of galaxy formation, which assumed a slower, more gradual process. Instead, it hints at a universe that kicked off its cosmic construction with a bang, building colossal galaxies almost instantly. The implications are profound. If these ancient galaxies were already enormous, it changes how we trace the evolution of stars, dark matter, and the cosmic web. But how did Webb uncover these hidden stars? By detecting their faint, infrared light, which has been stretched over time. This light reveals stars that were previously shrouded in dust, allowing scientists to peer deeper into the universe's infancy than ever before. The data suggests these early galaxies were not just larger but also more active, with intense star formation rates that defied previous expectations. This isn't just about size, it's about rethinking the timeline and mechanisms of galaxy birth. The universe, it seems, was a far more dynamic and ambitious place in its youth than we ever imagined. As we piece together these revelations, one thing is clear: the story of the cosmos is still unfolding, and every new discovery brings us closer to understanding its origins. If you've enjoyed this deep dive into the secrets of the early universe, hit that subscribe button for more explorations of space's greatest mysteries. And if you have questions or theories about how these ancient galaxies formed, drop them in the comments. We'd love to hear your thoughts. The universe is full of surprises, and the journey to uncover them is just beginning.